Welcome to the deep dive. We try to make complex stuff make sense fast. Today, we're diving into something really fundamental: 3D space, vectors, surfaces. Basically, the building blocks for describing, well, almost everything physical. We're using Chapter 12 of Calculus, Early Transcendentals by Stewart, Clegg, and Watson as our guide, our mission. Cut through the textbook jargon, get to the core ideas. Whether you need a quick refresher, you're exploring this for the first time, or maybe you're just curious, we want you to walk away feeling like you get it.
Absolutely. And this chapter, it's more than just math formulas. It's really about learning the language to describe our three-dimensional world. It sets the stage for everything that comes later in calculus when you start dealing with curves moving through space or complex surfaces. It's foundational.
Okay, so let's start simple, or simple-ish. We all know how to find a point on a flat map, right? X and Y coordinates? Easy. But the real world isn't flat, so how do we locate something in, actual space?
Right, you need that third dimension, depth or height. So instead of just xy, we need three numbers, x, y, z.
Altitude, basically.
Kind of, yeah. We set it up with a starting point, the origin, O, then three lines, axes, all meeting there, and all perfectly perpendicular to each other. Your x, y, and z axes. Think of x and y making the floor and z going straight up.
Okay.
And to make sure we're all oriented the same way, there's the right-hand rule. If you curl the fingers of your right hand from the positive x-axis over to the positive y-axis, your thumb points straight up in the direction of the positive z-axis. It just keeps things consistent.
That's actually a neat trick. So, imagine you're standing right in the corner of a room, bottom corner. That's your origin.
Exactly. The floor is the z-plane.
Okay.
The wall to your, say, left is the x-plane. The wall to your right is the y-z plane. Those are the coordinate planes.
And they slice up space into 8 sections.
8 octants, yeah. And where you're standing with positive x, y, and z, that's the first octant.
Got it. So finding a point like PABC is just moving A along X, B parallel to Y, C parallel to Z, like giving directions.
Precisely. And we can talk about projections, too. If you shine a light straight down from PABC, its shadow on the floor of the z-plane is the point QAB0. That's its projection onto the z-plane.
Okay, projections make sense. Now, here's something that always took me a second. Equations in 3D. They're not lines anymore.
Right. That's a huge conceptual leap. In 3D, an equation typically describes a surface. Take z quiz. It doesn't mention x or y. That means any point works as long as z coordinate is 3. So it's a flat, infinite plane floating 3 units up, parallel to the z-plane floor.
Wow, okay, so Y5 would be like a vertical wall parallel to the XZ plane.
Exactly. And think about axes too. In 2D, that's just a vertical line.
But in 3D, it's a whole plane slicing through X to D. Infinite wall. Whoa.
Yeah. And combinations get cool. X up plus 1, A and D, Z equals 3.
X up plus 1 me equals 4 is a circle in 2D. So a circle, but lifted up to Z3.
Perfect. A circle of radius 1 sitting flat on that Z3 plane.
Okay.
But now what if you just have X swap plus 1, 1, 1 and no rule for Z?
Z's can be anything. So the circle just stretches up and down.
Exactly. It becomes a circular cylinder, an infinite tube following the Z-axis.
Okay. So the missing variable is key.
That's the giveaway for a cylinder. Its rulings, the lines making it up, run parallel to the axis of that missing variable.
Right, right. And how do we measure distance between points up here in 3D? Is it like Pythagoras again?
It is. The distance formula in 3D is just a direct extension. You square the differences in x, y, and z, add them up, and take the square root.
So distance between P2 91.7 and Q1 93.5. Let's see. Difference in x is 1, squared is 1. Difference in y is 2, squared is 4. Difference in z is 2, squared is 4. Add them up. 1 plus 4 plus 4 is 9. Square root 3.
You got it. Simple as that.
Okay, that's not too bad. Now, spheres. If you take all the points that are, say, 5 units away from a central point, that's a sphere.
That's the definition, yeah. A set of points equidistant from a center, CHKL, and that leads straight to the equation of a sphere. XH plus YK plus ZLR is the radius.
It's just like the circle equation, but with the z term added.
Exactly. If the center is the origin, it's even simpler. X subs plus 1 plus y plus up plus is to what you'll.
And sometimes they give you a messy equation, right? Like all expanded out.
Yeah, like x sub plus y plus z bone plus 4 by 6y plus 2z plus 6 plus z. Doesn't immediately look like a sphere.
Ugh.
But you can use that technique, completing the square, for the x terms, the y terms, and the z terms separately.
Right. Group them. Add the magic number to make a perfect square.
And when you do that here, you rearrange it into x plus 2 buckle plus y to 3 buff z plus 1 plus 8.
So the center is -2, 3, -1, and the radius is square root of 8, which is 2 root 2.
Perfect. You just uncovered the sphere hidden in the algebra.
Cool. So this whole section, 12.1, it's really just setting up the stage, right? Defining our 3D coordinate system.
It's the absolute foundation. You need this spatial understanding before you can talk meaningfully about anything moving or existing in 3 dimensions. It underpins chapters 13 through 16, definitely.
Okay, now for the really fun stuff.
Yeah.
Vectors. These seem to pop up everywhere. Physics, engineering.
They do. Because so many things in the real world don't just have a size, they have a direction too. Think about velocity, how fast and which way. Or force, how strong and in what direction.
Right. Like wind pushing a boat. It's not just how hard the wind blows, but where it's blowing from.
Precisely. So a vector is a quantity with both magnitude, the size, length, strength, and direction. This makes them different from scalars, which are just numbers like temperature or speed, not velocity.
And we draw them as arrows.
Yep. Length of the arrow shows the magnitude. The way it points shows the direction. The start is the tail. The end is the tip.
Okay. And if two arrows have the same length and point the same way, they're the same vector, even if they're in different places.
Correct. They're equivalent or equal vectors. They represent the same displacement or force, regardless of the starting point. And there's the zero vector, which has zero length and no specific direction.
How do you add them? If I push something east and you push it north, what happens?
That's vector addition. 2 main ways to visualize it. The triangle law. Put the tail of the second vector at the tip of the first vector, u. The sum, u plus v, is the arrow going from the original tail of u straight to the final tip of v.
Like connecting the dots of the journey.
Exactly. Or the parallelogram law. If u and v start at the same point, draw a parallelogram using them as adjacent sides. The sum u plus v is the diagonal starting from that same point.
Ah, okay. And it doesn't matter which order you add them. U plus v is the same as v plus u.
It is. Vector addition is commutative.
What about multiplying by a number? Like 2 times a vector?
That's scalar multiplication. Multiplying by a scalar, just a real number, scales the vector's length. So 2v is twice as long as v, same direction.
And v.
Same length as v, but exactly the opposite direction.
Okay. And if one vector is just a scalar multiple of another, they're parallel.
That's the definition of parallel vectors, yes. They point along the same line, either in the same or opposite direction.
And subtracting, u minus v.
You can think of vector subtraction as adding the negative. uv yields u plus any v. Geometrically, you just flick around and add it using the triangle or parallelogram law.
This visual stuff is helpful, but how do we actually calculate with these?
That's where components come in. This is the game changer. Place the vector's tail at the origin, 0, 0, 0. The coordinates of its tip, a1, a2, a3, are its components. We write the vector as a1, a2, a3.
Ah, so you turn the arrow into just numbers.
Exactly. And if a vector doesn't start at the origin, say it goes from point A, x1, y1, z1, to point B, x2, y2, z2, its components are just the differences. a2 by 1, y2, y1, z2, z1, terminal point minus initial point.
Okay, that lets us define any vector with numbers, and its length, its magnitude.
That's just the 3D distance formula applied to its components. The magnitude A is GART T, A1 plus A2, or plus A3, B3. Nice, so now we can do math. Add vectors just by adding components.
You got it. To add A1, A2, A3, and B equal B1, B2, B3, the sum is A1 plus B1, A2 plus B2, A3 plus B3. Subtraction works the same way. Scalar multiplication, just multiply each component. CA equals phi A1, C2, CE3. That makes everything way easier. Geometry becomes algebra.
It really does. And this idea extends beyond 3D. We talk about Vn for n-dimensional vectors, you know, like in relativity theory where you have space-time vectors, x, y, z, t.
Whoa, okay. Stick to 3D for now.
Ah.
Are there, like, basic building block vectors?
There are. The standard basis vectors, I, j, and ki, is 1, 0, 0, just one unit along the x-axis. J is 0, 1, 0 along the y-axis. K is 0, 0, 1 along the z-axis.
So they're like the fundamental directions.
Exactly. And any vector A1, A2, A3 can be written as a combination, A1i plus A2j plus A3k. It's just another way to write it using these basis vectors.
And sometimes you just need the direction, not the length.
Right. For that, you find the unit vector. That's a vector with length 1. To get the unit vector in the same direction as a vector A, you just divide A by its own magnitude, UEA.
Okay, that makes sense. Normalize it.
Yep. Now, applications. Think about forces. If 2 wires are holding up a weight, the tension in each wire is a force vector. The total upward force from the wires has to exactly balance the downward force of gravity, the weight. We can break down the tension vectors into horizontal and vertical components using trigonometry, set up equations based on equilibrium, net force is 0, and solve for the unknown tensions. It's a classic physics problem solved with vectors.
Right, resolving forces. And velocity too, right? Like a plane flying in wind.
Perfect example. The plane has its own velocity vector relative to the air. The wind has its velocity vector relative to the ground. The plane's actual velocity relative to the ground is the vector sum of those two.
So the pilot has to account for the wind vector to actually go where they want to go.
Absolutely. Or think of a boat crossing a river with a current. The boat's engine provides one velocity vector, the current provides another. The resulting velocity is their sum. If you want to go straight across, you actually have to aim slightly upstream to counteract the current. Vectors let you calculate exactly how much.
This is really powerful stuff. It connects the geometry to actual physical problems.
And it's the foundation for Chapter 13, where we start talking about vector functions to describe motion along curves.
Okay, so we can add, subtract, scale vectors. Can we multiply them?
Well, yes, but there are two different kinds of vector multiplication, and they give very different results. First up is the dot product.
Dot product. Okay, what does it do?
It takes two vectors, say A and B, and gives you back a single number, a scalar. That's why it's also called the scalar product.
A number, not a vector. How's it calculated?
Algebraically, it's super easy. If A1, A2, A3, and B1, B2, B3, then AOB equals A1, B1 plus A2, B2 plus A3, B3. Just multiply corresponding components and add them up.
Huh. Okay. Simple enough, but what does that number mean?
That's the cool part, the geometric interpretation. It turns out that AOB is also equal to AB cosi, where cosi is this angle between the two vectors when placed tail to tail.
Oh, okay. Cosine and the angle.
Yeah.
So the dot product is related to the angle between them.
Directly. It tells you how much they're aligned. If they point in roughly the same direction, for cos is positive, so the dot product is positive. If they point in roughly opposite directions, obtuse, cos is negative, dot product is negative.
And if they're perpendicular, cos is 90 degrees, or 2 radians. Cos 90 degrees is 0.
Exactly. So if we is 0, then the vectors A and B must be orthogonal, perpendicular. Assuming neither is the 0 vector, of course. This is a massively useful property. A quick calculation tells you if things are at right angles.
So you can find the angle too. Just rearrange that formula.
Yeah.
Cos is AB, AB.
Yeah, calculate the dot product, calculate the magnitudes, divide, gives you the cosine of the angle, then find the angle itself.
Okay, orthogonality is huge. What else can we do with this? You mentioned projections earlier.
Right. The dot product is key for projections. Imagine you want to find the shadow of vector B onto vector A. How much of B points in the direction of A? That shadow length is called the scalar projection of B onto A, written cum supa sub B. And the formula is cum supa sub B equals AOBA.
Just the dot product divided by the length of the vector you're projecting onto.
Exactly. And if you want that shadow as an actual vector with direction, that's the vector projection, prime supa sub B, you just take the scalar projection, the length, and multiply it by the unit vector in A's direction. So prime supa sub B, AOBAA.
Okay, scalar projection is the length. Vector projection is the actual shadow vector.
Got it.
Applications.
Physics. Remember work. Basic definition is force times distance W if AD.
Yeah, but that only works if the force is exactly in the direction you're moving.
Precisely. The dot product fixes that. Work is the dot product of the force vector F and the displacement vector D, W equals FUD.
Because FD cosi, it automatically finds the component of the force along the displacement and multiplies by the distance.
You nailed it. So if you're pulling a wagon with a rope at an angle, the dot product tells you how much work you're actually doing to move the wagon forward. Super useful.
Okay, dot product gives a scalar, relates to angle, finds projections, calculates work. What's the other way to multiply vectors?
That's the cross product, written AXB. And this time, the result is not a scalar, it's another vector. And critically, this new vector is perpendicular to both A and B.
Whoa, perpendicular to both. How does that work in 3D?
It only works in 3D. If you have two vectors A and B that aren't parallel, they define a plane, right?
Yeah.
The cross product AXB gives you a vector sticking straight out of that plane perpendicular to it.
Okay, that's useful. How do you calculate that?
It's a bit more involved. It's often defined using determinants, which is kind of a calculation shortcut. For A, A1, A2, A3, and B as components involving combinations like A2B3, A3B2.
That's messy.
It is a bit, but the structure is memorable with the determinant trick. The key thing isn't the formula right now, it's the properties. First property, AXB is orthogonal to A and orthogonal to B.
So perpendicular to both.
Okay.
But perpendicular could be pointing up or down relative to the plane they define. Which way does it go?
Another right-hand rule. Point your fingers along A, curl them towards B through the smaller angle. Your thumb points in the direction of AXB.
Okay, consistency again. What about the length of this new vector, the magnitude AXB?
That also has a neat geometric meaning. AXB equals AB sin. Notice the sign this time, not cosine.
Yes, okay.
And this magnitude, AB sin, turns out to be exactly the area of the parallelogram formed by vectors A and B when they start at the same point.
Wow. So the cross product's length gives you an area.
Yep, which means you can find the area of a triangle defined by 3 points in space. Just take half the area of the parallelogram formed by 2 vectors along its sides.
That's handy. And what if the cross product is 0? AXB is the 0 vector. That means sin must be 0.
Which means is 0 or 180 degrees, so.
They're parallel.
Exactly. AXB equals 0 if and only if A and B are parallel. That's another useful check.
Okay. Important properties. Gives a perpendicular vector, right-hand rule for direction, magnitude is parallelogram, area 0 if parallel. Is it commutative? Is AXB equals BXA?
No. It's anti-commutative. AXB equals BXA. Swapping the order flips the direction of the resulting vector.
Right, because the right-hand rule would make your thumb point the other way. Okay. Applications. Besides area.
Finding a vector perpendicular to a plane is a big one. If you have 3 points P, Q, R in a plane, you can form vectors PQ and PR. Their cross product, PQX, PR, will be a normal vector to the plane. Super important for defining planes.
Normal vector. We'll need that later, I bet. Any physics applications?
Absolutely. Torque. Torque is the rotational force, the twisting effect, like using a wrench.
Longer wrench, more torque.
Exactly. And torque is defined as a cross product, equals RXF, where R is the position vector from the pivot point, the bolt, to where the force F is applied on the wrench handle.
So it's a vector too, the torque.
Yes. The direction of the torque vector tells you the axis the object wants to rotate around, again, right-hand rule, and its magnitude, RF sin, tells you how strong that twisting effect is. The sin explains why applying force perpendicularly gives the most torque.
That makes perfect sense. Cross product seems really tied to rotation and orientation.
It is. And there are also triple products, like the scalar triple product, AYO-BXC. Its absolute value gives the volume of the parallel pipe the slanted box formed by the 3 vectors A, B, C.
Volume from vectors. Cool.
And if that triple product is 0, it means the volume is 0, so the 3 vectors must lie in the same plane. They're coplanar.
Okay. Vectors, dot products, cross products. We have a lot of tools now. How do we use them to describe basic shapes like lines and planes in 3D?
Good question. Let's start with lines. What do you need to uniquely define a line in space?
Maybe 2 points on the line.
That works. Or, equivalently, 1 point on the line, PO0, X0, 0, 0, 0, 0, and a direction vector V equals ABC that's parallel to the line.
Okay, a point and a direction, like a starting location and a heading.
Exactly. Let R0 be the position vector of P0 and R be the position vector of any point P on a line. Then the vector from P0 to P, which is R0, 0, must be parallel to V.
Meaning R0 is a scalar multiple of V.
Precisely. RR0, 0 is TV for some scalar t. Rearranging gives the vector equation of a line, R equals R0 plus TV.
And R, R0, V are vectors. T is a parameter. As T varies, you trace out the whole line.
If you write out the components, you get the parametric equations. X0 plus at, YY0 plus BT, 0, 0 plus CT. These numbers A, B, C in the direction vector are called direction numbers.
Okay, vector equation, parametric equations, any others?
If none of A, B, C are 0, you can solve each parametric equation for T and set them equal, giving the symmetric equations X, X0A, YY0B, 0, 0C. It's just another form.
Got it. And if you only want the piece of the line between 2 points, say for T between 0 and 1,
that defines a line segment. Restricting the parameter t gives you finite parts of the line.
What about those lines that aren't parallel but never cross?
Skew lines, a purely 3D phenomenon. They exist in different planes and just miss each other entirely.
Weird. Okay, that's lines. What about planes? How do you define a flat surface in 3D? A point and a direction isn't enough.
Right. A direction vector would just define one line in the plane. For a plane, you need a point P0, X0, 0, 0, 0 in the plane, and crucially, a vector n equals ABC that is normal, orthogonal, perpendicular to the entire plane.
A normal vector, sticking straight out of the plane.
Okay, now take any other point P, X, Y, Z in the plane. The vector from P0 to P, let's call it RR0, must lie in the plane. And if n is perpendicular to the plane, it must be perpendicular to every vector lying in the plane. So
n must be perpendicular to RR0. Their dot product must be 0.
Exactly. N RR0 plus 0 plus C0, 0 plus CZ0, 0, 0, 0. It's the scalar equation. Often you multiply it out and rearrange it into the general form x plus y plus cz plus d equals 0. The coefficients a, b, c are always the components of the normal vector.
So if I see an equation like 2x plus 3yz equals 5, I instantly know that 2, 3 minus 1 is a normal vector to that plane?
You got it. And if you have 3 points that are in a line, you can find the plane containing them. Make 2 vectors between the points, like PQ and PR, take their cross product.
You get the normal vector in. Then use one of the points as P0 and plug into the scalar equation.
Perfect.
What about planes interacting? Parallel planes.
Easy. Their normal vectors must be parallel. So n1 is just a scalar multiple of n2.
And if they're not parallel?
They intersect in a straight line.
Makes sense. Can you find the angle between them?
Yep. The angle between planes is defined as the acute angle between their normal vectors, n1 and n2. You can find it using the dot product formula for angles.
Okay. And finding the actual line at intersection seems complicated.
It takes a few steps, but you basically need to find a point on the line. By solving the 2 plane equations simultaneously, maybe setting z0 to start and the direction vector of the line, which must be perpendicular to both normal vectors, so you can get it from n1 and n2.
Cross product again. Okay. Last thing here. Distances, like point to a plane.
Yep, there's a formula for the distance from a point, I01, Y1, Z1, to a plane X plus by plus CZ plus D equals 0. It's dxx1 plus by1 plus CZ, Z1 plus D squared to A plus B plus CR. It looks intimidating, but it's plug and chug.
Absolute value on top.
Yeah.
Square root of the normal vector's magnitude squared on the bottom.
Okay, and distance between parallel planes. Just pick any point on one plane and find its distance to the other using that formula.
And those skew lines, can you find the distance between them?
Yes. The shortest distance between 2 skew lines can be found by seeing them as lying in 2 parallel planes and then finding the distance between those planes. It often involves the scalar triple product.
Wow. Okay, lines, planes, distances. We can really map things out now. What's next? More complex surfaces.
Exactly. Section 12.6 deals with cylinders and quadric surfaces. And a key tool here is using traces.
Traces? Like footprints?
Sort of. A
Yeah.
trace is the curve you get when you intersect the 3D surface with a plane, usually one parallel to the coordinate planes, like setting xk or yk or zk. By looking at these 2D cross-sections, you can figure out the 3D shape.
Like slicing an orange at different heights to see the circular cross-sections.
Perfect analogy. We already talked about cylinders, remember? The key is a missing variable in the equation. Z executor is a parabolic cylinder because y is missing. Exequa plus y is a circular cylinder because z is missing.
Right, the rulings run parallel to the missing variable's axis.
Now for the quadric surfaces, these are the 3D versions of conic sections. Circles, ellipses, parabolas, hyperbolas. They come from second-degree equations in x, y, and z. There are 6 basic types.
6. Okay, let's try.
First, the ellipsoid. Its equation looks like XO plus YB plus Z star C equals 1. All its traces, slicing parallel to the XOYZ or XC planes, are ellipses. If ABC, it's just a sphere.
Like a stretched or squashed sphere.
Got it. Then, the elliptic paraboloid, like ZC XO plus YB co. Think of a bowl shape. Horizontal traces, aka are ellipses. Vertical traces, xk or yk, are parabolas. The variable raised to the first power z in this case tells you the axis the paraboloid opens along.
Bowl shape, okay. Ellipses and parabolas.
Next, the tricky one. The hyperbolic paraboloid. Like zc is xcyybg. This is the saddle shape. Horizontal traces are hyperbolas. Vertical traces are parabolas, but opening in opposite directions.
The Pringles chip shape.
Yeah.
Saddle. Got it. Hyperbolas and parabolas.
Yep. Then the hyperboloid of one sheet, like xa upon slice y vbc, so report east 1. Notice 1 minus sign. Horizontal traces are ellipses. Vertical traces are hyperbolas. It's one connected piece, often looks like a nuclear cooling tower. The axis corresponds to the variable with the minus sign, z here.
Cooling tower, one piece. Ellipses and hyperbolas.
Compare that to the hyperboloid of 2 sheets, like Nasterway, Saramal baby plus C Sarah YRB1, 2 minus signs. This one comes in 2 separate pieces, like 2 bowls facing away from each other. Horizontal traces are only ellipses if z is large enough, nothing in between. Vertical traces are hyperbolas. The axis corresponds to the variable with the positive term, z here.
2 bowls, 2 pieces. Ellipses, sometimes, and hyperbolas. Okay, last one.
The cone, like Zusiko of Cool's Xor Sala plus YOBB, it was like, well, a cone, actually a double cone meeting at the origin. Horizontal traces are ellipses. Vertical traces through the origin are pairs of intersecting lines. Other vertical traces are hyperbolas.
Okay, 6 types. Ellipsoid, elliptic paraboloid bowl, hyperbolic paraboloid saddle, hyperboloid of 1 sheet cooling tower, hyperboloid of 2 sheets, 2 bowls, cone. identified by their traces?
Exactly. And sometimes you need to complete the square first to recognize which type it is if the equation is messy.
And these aren't just abstract shapes, right?
Not at all. As you said, the Earth is an ellipsoid. Satellite dishes are circular paraboloids that shape perfectly focuses incoming parallel signals like radio waves to a single point, the receiver.
Ah, that's why they're shaped like that.
And those hyperboloids of one sheet. Used in cooling towers partly because that shape is very strong structurally for its surface area.
Amazing. So this math really does describe the shapes around us.
It truly does. We've gone from just plotting points in 3D to using vectors for forces in motion, defining lines and planes, and now visualizing these complex quadric surfaces. It's a whole geometric language.
It really is a journey. We covered a huge amount of ground 3D coordinates, vectors, dot and cross products, lines, planes, cylinders, quadrics.
And the key takeaway is how these tools let us model the real world, whether it's physics, engineering, computer graphics, even economics or biology sometimes. This mathematical framework is essential for describing and solving problems in 3 dimensions. It really opens the door to understanding so much more complex phenomena later on.
So thinking back on this deep dive into Chapter 12, what concept really clicked for you? What was the biggest aha moment about how we describe space and vectors? It's definitely given me a new appreciation for things like torque and satellite dishes. A huge thank you for joining us on this exploration. Last Minute Lecture team, warm thank you from the Last Minute Lecture team.